Okay, welcome to my channel Physics Matters. Today I would like to talk about two important quantities in physics, and this is speed and velocity. And we will see that they are actually very similar. In some cases they can even be the same, but we will go now through it step by step. And the easiest one that we can define is actually the speed. The reason for this is that it is only happening in one dimension. So we can, for example, take here any point A and here any point B, and we can draw now a straight line through these points. So let's do it in red. Then this is called the distance between these two, because we can actually define the distance, this term distance, as the shortest connection between A and B. And if once we have defined this distance, we can then go to the next step and define the speed of an object as the fraction distance over time. Or if we want to use the this letter d for the distance, we can write d over t, because t stands for the time. And this is also the most natural way how to define speed, because if, for example, the distance increases and the object moves along this distance in the same time, it means that the speed of this object also increases. And if, on the other hand, the time increases that this object needs, then, because time is standing in the denominator, the speed actually decreases if the distance is constant. And which means that the object is just moving slower. And we can make a simple example from that. For example, we have a car. And this car moves with a certain speed. So let's suppose this speed is unknown. We don't know exactly how fast the car is, but we know the distance that the car travels. So in this case, for example, 100 kilometer from one city to another, for example, and the time that it takes is 2 hours. So the speed that this car has, we can actually simply calculate as d over t in the same way how we have defined it before. And then we can insert our 100 kilometer and we can insert here our 2 hours. And this gives at the end a value of 50 kilometer per hour. If sometimes the speed is given and the time, or the speed and the distance, then we have to calculate the third parameter from the other two. And in order to do this, we can of course always solve this equation for d and for t, but there's also a possibility to memorize this a little bit easier. So I can just give you a small idea. For example, you can use this kind of triangle here to write down v in the lower left corner, t in the lower right corner, and d, the distance, in the upper corner. So now, if we, for example, want to calculate v, the speed, then we can take this horizontal line as a fraction line, and we can write here d over t. Or we can, for example, calculate the distance as v, because they are standing in the same line, v times t. Or, of course, we can also calculate this time, very similar, as d over v. This is a very nice way how to actually do this kind of calculation very fast. Now, as you have seen, we have used kilometer per hour before, but the standard units are of course meter per second. So we have to do something which is called unit conversion. And we have to convert one unit into the other. And this we can do in the following way. Let's suppose we have here our speed given in meter per second. Then we want to find any constant that is able to transfer this into our speed in kilometer per hour. So in order to do that, we can write now v equal to 1 kilometer per hour, and we know 1 kilometer is equal to 1000 meter, and 1 hour is nothing else than 3600 seconds. And a lot of these powers of 10 cancel out, and at the end, when you do the math, you find out that only 1 over 3.6 remains, and of course the unit meter per second. So now we can say that if we have a value given in meter per second and we want to convert it into kilometer per hour, we have to multiply it with 3.6. Or in other words, we can write v in kilometer per hour is equal to 3.6 times v in meter per second, and the other way around is also true. Then we have to divide it by 3.6. So an example, it's actually very simple. V could be, for example, 10 meter per second. So we have to multiply it with 3.6, and at the end we get our v is equal to 36 kilometer per hour. Until now we have only looked at the cases where the speed of the object is constant. And if this is not the case, then we have to introduce a new term which is called momentary speed. And what does it mean? So in order to explain this, I would like to draw something which I call distance time diagram, which could look, for example, similar to this. We have on the x-axis we have our time in seconds, and on the y-axis we have our distance. And if we assume that the object just moves along the x-axis, we can just write here x in the units of meter. And now we can draw a few lines into this diagram just to understand it better. So let's suppose we have here a horizontal line. This means that our x value remains constant within time. And if delta x is 0, then of course our speed must be also 0. This line illustrates an object that is not moving. And now we can also draw, for example, two other lines, for example this one and this one. The x coordinate changes within time. So here we can say that x increases, so we know that the speed must be larger than 0, and here the x value decreases, so v must be smaller than 0. And if we want to quantify this, we can here now draw this triangle here to determine the slope. Then this would be delta x and this would be delta t. And then we can define here for the constant speed, the speed v as delta x over delta t. Yeah, and this is just the standard definition of speed. So here we didn't have any, or we didn't learn anything new, but now our case is a little bit more complicated, and now, because now our speed changes within time. So again, we have here our time on the x-axis and our x position on the y-axis. And we can now draw a graph which could, for example, look like this. Now we can see that we don't have a straight line. Of course, we can still draw a line from one endpoint to the other. Let's suppose this is point A and this is point B. And then we can calculate the slope similar to how we have done before as delta x over delta t. And what we get then from that is the average speed of our object. So if the speed is constant, it's the exact speed, but if the speed is not constant, as in this case, then we can only define an average speed in the way that we write delta x over delta t. Or in other words, delta x over delta t gives the exact speed if the speed is constant, and an average speed if the speed changes within time. However, we are more interested at the moment in maybe calculating the momentary speed at a certain point, for example here, and this we can call c. And in order to do that, we have to draw a tangent through this point, and then we can also calculate the slope, again similar to here, as delta x over delta t. But because we want to calculate the slope at that certain point, it is clear what we need. It is actually the derivative. So what we can do for the momentary speed, we can write v equals, and then we have to come from that direction and from that direction. So in this case, we can write v equals limit delta t approaching 0 of delta x over delta t. And this is of course nothing else except the derivative of x with respect to t. So our deltas turn into these, and we can just write dx over dt. Or we can also write it in other forms, for example, x dot. This is the way how physicists usually like to write it. Engineers prefer dx over dt, but physicists as well. And mathematicians, they would now write x prime of t. This is the definition of our momentary speed. And we can also give a short example. For example, if our x value, this must be now a function of time, otherwise we cannot calculate the derivative, is equal to, for example, minus 5 meter per second t square plus 10 meter per second t minus 20 meter. And the reason why we have here meter per second square is because here we have a second square, and it has to cancel out at the end in order to make sure that only the unit meter remains for our x position. So now we want to calculate the speed from that v, and then we have to calculate the derivative, as I said before. So we have to calculate dx over dt, and this is minus 5 meter per square second t square. So this t square turns into 2t, and we can write minus 10 meter per square second t plus 10 meter per second. This t vanishes, and the constant here is also equal to 0. So this would be the momentary speed v, which is also a function of t, by the way, if our x of t is given. And the last step which is missing is that we go from 1 dimension into 3 dimensions, and then we come to the term velocity. And this is very similar to our speed, as I said before. So you can actually describe it as an absolute value. Absolute value plus a direction. And this absolute value we know already, of course. This is our speed. So the speed plus the direction gives the velocity, and this means that it is actually also a vector quantity. So the speed is a scalar and velocity is a vector quantity. And what we can do with this, we can now actually make a diagram, coordinate system, where we have here our x-axis, y-axis, and our z-axis. And we can draw any arbitrary vector in that, for example here, any vector r. And yeah, this is our space vector. And now we also have, of course, certain unit vectors. So for example, here we have the unit vector in Z direction, and we write a small hat on top of that. Here we have our unit vector in Y direction, and here we have our unit vector in X direction. Okay, and then we can, of course, as we know already, we can write this vector R as a linear combination of the X value of this vector times the unit vector in X direction plus the Y value times the unit vector in Y direction plus the Z value times the unit vector in Z direction. Yeah. So if our vector is given as X, Y, Z, then we have to calculate the derivative in order to get the velocity. Yeah? So our V will be then simply given as, very similar to what we have written down before, dr over dt. And as you can see here, our unit vectors are constants, they are not changing, so we only have to calculate the derivatives of these x values, y values, and z values. And because it's a linear combination, we can calculate this for every term individually, which at the end turns into dx over dt, dy over dt, and dz over dt. Yeah? Nothing else. And this gives us a new vector, which is the velocity vector. And in order to make this more clear, we can, of course, again note down a small example. We can, for example, have a vector r as a function of t with the values 3 meter per second square times t square. Again, the reason for t, again the reason why we have here s square, second square, is because we have a t square here. 3 meter per second t square, and the second one could be, for example, minus 5 meter per second t, and here we could, for example, just write 7 meters as a constant. Then our velocity v would be again, so let's write v over t, would be again dr over dt. And then, as I said before, we can calculate the derivatives individually. So this would give us 6 meter per square second t. This would give us a minus 5 meter per second, because this t vanishes. And the last one is a constant, so we can just write here a 0. Okay, this is now our momentary velocity at any given time t. And if we want to calculate this for a specific time t, then we can write it in the following. So velocity at time t equals to 5 seconds, we can write v of 5 seconds, and this would be dr over dt at the position 5 seconds, and this is 30 meter per second, because t here equals 5. 5 times 6 is 30, and the same here leads to minus 25 meter per second, and here at the end we get again the value 0. So this is in principle everything what you need to know regarding speed and velocity in order to do any kind of calculations with that. I hope that this was beneficial. Thank you very much for your attention, and see you for our next video.